So in this video, we'll cover electron affinity, electronegativity, and melting point. Those are the physical properties that we have left over. And then we're also going to look at chemical properties of alkali metals and oxides of period 3. If you looked at the post on Google Classroom, you would have seen that I directed you to do the warm-up first and then to watch another video, and that video is on electron affinity, and answer the questions that I have in the slides. So really what this video is going to look at, or what I'm going to talk about, are this last thing. So electronegativity, alkali metal, melting point, blah blah blah. Okay, and that's from slide 12 onwards. So let's get that done. So what is electronegativity? Electronegativity is actually used to explain a lot of the other physical properties. Itself, the definition is the ability of atoms to attract a bonded pair of electrons in a covalent bond. If we have, say, chlorine and chlorine bonded together, there are two electrons that are being shared, one from this chlorine and the other one from the other chlorine. Let me just represent them. A dot and a cross. So if we have 7 from here and we have 7 from here, and they are sharing these two. Okay, so chlorine and chlorine are sharing these two electrons, and because they are the same thing, they share equally, right? But imagine if chlorine was sharing with hydrogen. So we have the 7 electrons of chlorine here, and then we have the 1 electron of hydrogen. These two are sharing these 2 electrons. So in this case, the sharing is unequal. The electrons will tend to spend more time next to one atom over the other one. So the property that explains this is called electronegativity. We say chlorine is more electronegative than hydrogen, which means that these electrons would rather, instead of spending 50-50 amount of time next to each of the 2 elements, they would rather spend time around chlorine. So chlorine attracts them to itself more than hydrogen attracts them. Okay, so we say chlorine is more electronegative. We have an electronegativity scale called the Pauling scale or Pauling scale, and there are some values that you can see. This can be found in the data booklet as well. So the higher the number, the more electronegative something is. And as you can see here, fluorine is the most electronegative element, and then chlorine is a little bit less, and bromine less, and iodine is the smallest. You can see the trend as you go down a group. Even in group 1, we start with 2.1 to 1.0, 1.0 and 0.9. And all the groups, we see the same thing. As you go down the group, the electronegativity decreases. Okay, when we go across in this direction, we can see an increase. So starting from lithium, beryllium, boron, carbon, nitrogen, oxygen, and finally fluorine, we see an increase as we go across. Going down the group, you guys could probably figure this out. Again, the thing that would attract electrons to a specific atom is the nucleus. So if you increase the number of shells, it means you are hiding the nucleus. There's too much shielding, so these electrons cannot be attracted because the nucleus is shielded, the thing that would pull the electrons. Okay, so as we increase the number of shells and increase the distance to the nucleus, we decrease electronegativity. Okay, and within a period, as we go across, we have the same number of shells, so the distance to the nucleus is about the same. But what is increasing in this way is effective nuclear charge. And because effective nuclear charge is positive in nature, as it increases, it has ability to pull electrons more. That's why elements on this side, like fluorine, are more electronegative than elements on this side. Okay, so I'll give you a moment here to write the trend and explain it to yourself. The next thing that we're going to look at is melting point. Melting point, and we're going to look at melting point for two groups. The first one is alkali earth metals, and the second one is halogens. For alkali earth metals, we'll come back to the proper explanation of why the trend is the way that it is. But it is important for this unit for you to know what the trend is. Maybe you won't be able to explain it properly, but you should know what the trend is. So as we go down the group, the melting point decreases. Okay, as we go down the group, the melting point decreases. Okay, for now, like I said, know the trend. You don't need to explain it. When we cover melting point in unit 4, then I will expect you to know how to explain this trend. Okay, same thing with group 7 or 17, sorry, the halogens. Even with this one, I expect you to know the trend, but you don't have to know why, because the reason why is covered in unit 4 when we do intermolecular forces, actually for both of them. So I expect you to know the trend, but not why it is the way it is. And in this case, the halogen case, it increases as you go down the group. So for alkali metals, it decreases as you go down the group. For halogens, it increases as you go down the group. Okay, so that's it for the physical properties. And now for the chemical properties. Again, just to remind you, chemical properties are largely determined by the number of electrons in the valence shell. Okay, so looking at group 1, alkali metals, we expect them to behave in a similar fashion, and they actually do. So let's look at some properties here. Physical properties, we have that they are good conductors of heat and electricity. Okay, they conduct heat and electricity. The reason why they conduct heat and electricity is also going to be covered better when we do metallic bonding in unit 4. But just so you know, IB cares a lot about you understanding why things conduct electricity. We don't really care too much about knowing why things conduct heat. I think that's more of a physics thing. Okay, so why do things conduct electricity, or what things conduct electricity? So whenever an object or a substance can allow a movement of charged particles, so charged particles such as electrons or ions, negative or positive. These are charged particles. Whenever we can allow free movement of such charged particles, then something conducts electricity. And how well it allows this movement tells us how good a conductor something is. Okay, so we're talking about electricity here. Okay, so we say metals are good conductors of electricity because they allow free movement of charged particles. Okay, and we'll see more about this when we do metallic bonding in unit 4. Okay, the next one is they have low densities. Density is mass over volume. So if something occupies big mass and small volume, we say it has big density. But metals, when they weigh less, they still occupy a lot of space. So that's why they have low density. It's like when you look at it, you would think it's heavier than what it actually is. That's what low densities mean here. And depending on whether I've already done this demo with alkali metals, you'll see that when it's freshly caught, it is very shiny. It is very shiny, and as soon as you allow it to stay exposed to air, then that fresh cut becomes covered with a layer of oxide, because the metals are very, very reactive. Okay, so they are shiny when freshly cut. You will see this. I will demonstrate this sometime during class. Okay, so for chemical properties, we know that they are very, very reactive. They are very, very reactive. That's why when you leave them out in the open, in just air, they will have a coat as soon as possible, because they'll react with the oxygen in the air, they'll react with the water in the air. So they are very reactive, and we will look at the trends in reactivity with these. Another thing is they form ionic compounds with nonmetals. They form ionic compounds with nonmetals. And what is an ionic compound? Again, we'll wait until chapter 4. Okay. What I do want you to know, what you do need to know, is that for alkali metals, when they react with water, they form hydrogen gas. And this reaction is very exothermic. In fact, sometimes you can experience an explosion when this reaction occurs, because our hydrogen gas here is very flammable, and if there's so much heat produced by the reaction, then it can actually catch on fire and explode. Okay, so this is the generic equation. This is just a generic metal, alkali metal, and this is water, forms metal hydroxide, okay, which is a base, metal hydroxide, and hydrogen gas. So what you expect to see here is some bubbles because of the hydrogen gas, but you also expect that the pH would be basic because it forms a metal hydroxide. Okay, so the last part is period 3 oxides. Okay, now this is where I told you guys we have quite a bit to memorize in this unit. So IB expects that you know the period 3 oxides, their formula, and their oxidation numbers, their electrical conductivity, and their structure. Okay, I got this table straight from the Pearson book, and this is really going to be mostly memorizing. Excuse me. Yes, it is memorizing, but there's a way to make it easy. It's not just memorizing. If you look at the oxidation numbers, they increase by 1 from Na all the way to chlorine. Yes, for the non-metals here, from phosphorus to chlorine, there are 2 numbers, right? There are 2 oxidation states. And yes, you need to remember that. And later on, when we talk about other parts of the content, we'll actually learn about how to figure out oxidation numbers. For now, I would say it's easier to memorize 1 all the way up to 7, and then for phosphorus there's another one which is 3, and for sulfur there's another one that is 4, and then for chlorine there's another one that is +1. Okay, the electrical conductivity with the metal oxides, they conduct electricity only when they are in their molten state or when they are liquid, like when you melt them and they become liquid. This is not solution, this is not dissolved in water, no. Even though if they are dissolved in water and they dissolve, they will conduct electricity. But molten is not dissolved, it's melted. Like you heat them up so high that they melt. Imagine salt at home, and you put it under fire until it melts into a liquid. That's what molten means. Okay, so the 3 metal oxides, they conduct electricity when they are melted. And then silicon here has very low conductivity, and the rest of them have none. Okay, so that means that when these guys are melted, they allow free movement of charged particles, because that's what electrical conductivity means. And then silicon dioxide allows very little, that's why the conductivity is very low. And then the non-metal oxides, they don't allow at all, so that's why they do not conduct electricity. Okay, so for the structure is giant 1, 2, 4. So giant ionic for the metal oxides, and then for this non-metal oxide, it's giant covalent, because for something to be ionic, there should be a metal and a non-metal, right? So that's why these three are all giant ionic. But this guy is giant covalent because it's a covalent bond. The rest of them are molecular covalent. So let's look at a structure of silicon dioxide here. Hopefully I can convince you that it is giant. So silicon dioxide is the same thing as glass or sand. Okay, sand and glass, they both have the same empirical formula as silicon dioxide. In fact, all silicon dioxide is this kind of giant structures. What do we mean by giant structure? So when you have silicon, okay, let's start with carbon dioxide. Carbon dioxide is carbon, oxygen 2, just like silicon is in group 4 or 14. Carbon is also in group 14, right? So, but carbon dioxide, if you draw its structure, it looks like this. We have carbon double bonded to oxygen and also double bonded to another oxygen. This is carbon dioxide. Simple. This one is called simple covalent because it's simple. We see where it starts and we see where it ends. Another word for simple covalent is called molecular covalent, which is a word that we just see, or a term that we just saw up here. So carbon dioxide, simple covalent. Okay. On the other hand, silicon dioxide, if you draw it, you have silicon. Silicon is joined to 4 oxygens. Okay. So it looks like it should be silicon tetraoxide because tetra is for 4. But each oxygen is connected to another silicon. So each oxygen is connected to 2 silicons, and each silicon is connected to 4 oxygens, and each oxygen is connected to 2 silicons, and each silicon to 4. So this, you can see that this structure can grow in many different directions almost uncontrollably. Okay, and this is the reason why we call it a giant structure, because I can keep drawing oxygens and silicons until kingdom come. There is no way to end this. The structure just keeps growing. That's why we call it a giant structure. While this structure here for carbon dioxide, we know where it starts and we know where it ends. This carbon atom and this oxygen atom and the other oxygen atom, that's it. But here, if I were to say, can I just isolate one silicon dioxide? It would be tough, because for me to be able to do that, I would have to maybe cut this oxygen and cut this oxygen and cut this oxygen and cut this oxygen so that I have silicon dioxide. And that is not something that we can do. So this is why silicon dioxide is called a giant structure, because it grows in all direction. And to be able to break off one silicon dioxide from another is impossible. Okay, it's not possible. So silicon dioxide is a giant covalent structure. Okay, for ionic compounds here, we also talked about them being giant. All ionic compounds are giant. All of them are giant, and that is because if you can think about drawing, let's see MgO, because that one is simpler. It's 1-to-1. Let's do MgO. If you have Mg, it's a positively charged ion, and then we have O, which is a negatively charged ion. So next to O on this side, we'll probably have Mg, because negative and positive want to be together, and negative they repel. So maybe you have an Mg here, and then O here, and then O here, and Mg here. So even this one, it grows from all directions, and it grows forever and ever. It does not end. It's hard to separate. Oh, this oxygen, it's hard to say this oxygen came from this Mg, because this oxygen is attracted to this Mg as much as it's attracted to that Mg. So the attraction within the quote unquote molecule and across molecules is the same. So ionic compounds are all giant, but covalent compounds, some are simple, some are covalent. Okay, this structure is very popular, and IB loves to ask for it in the test, because a lot of students will draw silicon dioxide like this. And I kid you not, I'm telling you right now, I'm going to ask this question in the test, and somebody's going to do this. Somebody in one of the two classes is going to draw this. I will ask this question in the test, and somebody's going to draw this. It happens every year, okay? So IB loves this question because every time somebody gets it wrong. So I'm telling you, you need to know the structure of silicon dioxide, and it's not that, okay? Moving on. I may ask for it in this unit or the next unit when we do unit 4 where bonding is concerned. So, okay, so moving on. The oxidation numbers. I may spend time when we are in class showing you guys how to do oxidation numbers, because I feel like doing it with a video is not good, because I won't be able to see whether you understand it or not. And it's not difficult. I'll show you later. Okay, so the other thing that you need to know is the acid-base properties of period 3 oxides. So we have the metal ones here, and we have the non-metal oxides. The non-metal oxides are acidic. Okay, easy. All of them are acidic. The metal ones, Na and Mg oxides, are basic, and then aluminum is amphoteric. For the basic oxides, so when you put them in water, they form metal hydroxide. So you can write an equation for that, okay? If you react a basic oxide with an acid, they form salt and water, which is a property of bases. When bases react with acids, they form salt and water, and that is called neutralization. Acidic oxides. When these acidic oxides, you put them in water, you form the acids like phosphoric acid or phosphorus acid, and then nitrous acid or nitric acid, and sulfuric acid and sulfurous acid. Okay, I will ask you guys to find these equations in either your textbook, actually Cognity, or your Pearson textbook, and write the equations here. These are important to know as well. You may realize here I wrote NOx and SOx because there can be NO and NO2. For SO is SO2 or SO3. That's why I put X here. And we cover this again in Unit 8 when we do acid deposition, like when we talk about acid rain. So you'll see this again then. But this is where you learn it. Okay, silicon dioxide does not react with water because it does not dissolve in water. But if you put it in with a very strong base, it forms a salt and water. That's why we say it's acidic, because it reacts with a base the same way that acids react with a base. But it has to be a very strong base. Okay, another one that is not soluble in water, aluminum oxide. Aluminum oxide is insoluble in water as well, just like silicon dioxide. Remember, silicon dioxide we said was sand or glass. So we know glass and sand do not dissolve in water, right? So same thing with aluminum oxide. But again, if we reacted with strong acids, it acts as a base. And if we reacted with strong bases, it acts as an acid. So again, please find the equations here that show that in your textbook. Okay, the last point is going to be melting point. It's going to be melting point. Okay. So I have this same table here because the structure tells us about melting point. So things that have giant structures, they have high melting points. And then things with molecular structures, they have low melting point. So hopefully, because you already have to know this and memorize this, the melting point just fits in that way. Okay, thank you.